unit, we learned how to figure out the shape of molecules. We're going to take that information now and go a step further. We want to figure out when a molecule is polar. We want to know when a molecule is polar because it has a lot to do with the way one molecule interacts with another, and that's going to affect how we understand these structural particles. So, last night's homework was to write the complete and skeletal structural formulas for the last two homework problems from the previous night. And those two homework problems were these two here. So we've got skeletal formulas, we've got complete structural formulas here, but we're going to write the condensed and skeletal formulas, okay? So the first one is just pentane. And there are 5 carbons here in a straight chain. This is a CH3, so a condensed structural formula for this starts with CH3. Then we've got CH2 here, CH2, CH2, 3 CH2s. Then finally on the end you've got another CH3. So this is the correct condensed structural formula for pentane. Okay? We're going to count this as each of these symbols is a point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 points. Okay? Okay, now the next one then is, let's see, this one here. I don't know if we named this one, but anyway, this is what we're going to do. So the first grouping is CH3. Then I've got CH here. There's a double bond between this CH and the next one. Then I've got a single bond. I don't have to show single bonds. I need a CH here. Then another double bond. Another CH. Another single bond, so I just put CH here. Another double bond. Then CH2 on the end. Okay, so that's another condensed structural formula. 1, 2, 3, 4, 5, 6, 7. Both lines are counting a point. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 22 points. So those are the two condensed structural formulas. Now we want to do the skeletal formulas. So we've got 1 bond, 2 bonds, 3 bonds, 4 bonds between carbons, and they're all single bonds. 1, 2, 3, 4. Whoop, I went too far. 1, 2, 3, 4. That's it. That's right. 1 bond, 2 bonds, 3 bonds, 4. That's it. Okay, so that's at each of the end of the line and every corner there's a carbon there, and you have to be able to figure out how many hydrogens belong there. On this carbon, there's 1 bond on this carbon on the end, so that there are 3 hydrogens. And this carbon here has a bond going to the left and the right, so there's 2 bonds already, so this carbon needs 2 hydrogens. So you infer the number of hydrogens based on the structure that you have here. But as far as the drawing, we just have 5 lines. 4 lines, okay? And so we're just going to make that 4 points. Okay? Does that make sense? All right, then let's go to the next one. You count, they lose a point. Okay? All right, so here I've got a bond between these 2 carbons. That's 1, 2, 3, 4, 5, 6 bonds between carbons. Okay? So that's 1, 2, 3, 4, 5, 6 bonds between carbons. That means there are 7 carbons. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7 carbons. Now we've got to figure out where the double bonds go. And they go between the second and third carbon. So there's 1, there's 2. This double bond goes here. And between the 1, 2, 3, 4, and 4th and 5th carbon, 1, 2, 3, 1, 2, 3, 4th and 5th carbon. and then between the 6th and 7th carbons, like that. Okay, so that's the skeletal structural formula. Now, it doesn't have to be that shape. I mean, you can flip it over, you can spin it around, you can make, zigzags like this if you want to, as long as you have the right number of lines and the correct placement of the double bonds. It doesn't really matter. All right, now let's count this way. This bond is going to be worth 1 point, and this is worth 2, because it's got 2 lines. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points. That's not what I got. Okay. Got 15 plus 4 plus 22 plus 9. Got a total of 50 points here. I mean, I'm just counting all the points on this, right? So I got a total of 50 points for everything. We have gone through all of the nomenclature that you need to know in this unit. What we need to do now is to make sure that you can figure out what kind of compound it is so that you can name it properly. Because remember, there are 4 different classes of compounds. Now, there are a few other little things to cover that we need to know about. And I'm going to spend a little bit of time with those right now. And then we'll eventually get to the point, probably later today, where we start actually just picking out names and figuring out how to figure out which category and then how to name it, okay? Huh? Now, before we get too far down the road, there is some structural stuff. Remember, we're drawing the shape of molecules in the last unit? We need to talk about how to figure out when you have a polar molecule, okay? You know how to figure out when you have a polar molecule, all right? So the first thing we have to do when we're figuring out if we have a polar molecule is figure out the shape of the molecule. And we did that in the last unit, okay? You had a lot of that on the last unit. You had to do that on the last test. So let's take, like, for instance, a simple molecule like water, okay? So if you don't have something to take notes on, you don't have your periodic table out, get that out now, because we're going to be practicing how to write and determine when you have polar molecules, okay? We're going to look at water first. Water is our first example. And what's the formula for water? H2O, okay? So we have 1 hydrogen, we have 2 hydrogens rather, and 1 oxygen. How many electron dots do we have on each of those elements? How many electron dots on a hydrogen? 1. How many electron dots on an oxygen? 6. And so we share electrons here and here, okay? And we get a Lewis dot formula. Okay, so this is started out with electron dot formulas, then we went to the sharing arrangement, and now we have a Lewis dot formula. Okay, from the Lewis dot formula we can figure out the actual shape of the molecule. We start with an electron pair shape, where we look at whatever look at whatever atom in that molecule is responsible for the shape. Okay, and that's usually a central molecule, but you have to, sometimes with more complex molecules, you look at more than one atom in that shape. In this class, it's almost always a simple molecule, so we're going to look at just what is in the center. Okay, so the oxygen is the center. It's the one that's responsible for the shape. And around this oxygen, there are 4 sets of electrons. And the shape we get when we have 4 sets of electrons is what? That was just the last unit. What's the shape you get when you have 4 sets of electrons? What? No, that's 3. Trigonal is 3. Tetrahedral. Okay, so we got one going up, one going 109.5 degrees out to the side, then one coming out toward you. We use a triangle to show that, and one going back behind. Okay, and so we're going to put our electron pairs on there those electron pairs that are around this oxygen here. Okay, it's 4 electron pairs, so we put 4 pairs around this. Okay, and the name of this is a tetrahedral electron pair shape. Okay, then the next step is to replace as many sets of electrons as are shared in the Lewis dot formula and replace them on this drawing. So you're going to redraw this exact same drawing. We're going to go back to our Lewis dot formula and look and see that we've got 2 pairs of electrons that are not shared, 2 pairs of electrons that are. So 2 of these pairs of electrons need to be replaced with the atom symbol. I'm going to replace this one and this one. Nothing special about those particular places. It's a little bit easier to see the shape of the molecule when you do that, but nothing special about it. That means that these 2 over here don't get replaced. They stay exactly as they are. Then you go to the last shape, which is to redraw exactly the same thing again. Now this is a tetrahedral electron pair shape here. I'm sorry, modified electron pair shape. This is the electron pair shape. This is the modified electron pair shape. It's a tetrahedral. The shape is the same. The only thing we've changed is the ends of the arms have something different on there. Then we redraw exactly the same thing over here. And once you've got exactly the same thing drawn over here, then you can erase the lone pairs. And we end up with a bent molecular shape. Okay? And that's how we figured out what the shape of these molecules were. Now that we have a shape, we can start figuring out whether it's polar or not. Okay? Now we can figure out whether it's polar or not. Let's put away the cell phones. Now to do that, then we need a reference in your test references called the periodic table of electronegativities. So find in your test references your periodic table of electronegativities. Yep. All right, now what we're going to look for are the numbers that are given for electronegativity. Let's remind you from Unit 2 what electronegativity is. It's a relative measure. That is to say, what we're saying is you take different combinations of atoms and you figure out how much those atoms pull on electrons when they share electrons between them. Okay, so these are electrons that are shared between 2 atoms here. Okay, and therefore shared between these 2 atoms here. And you figure out how much one atom's pulling on the electrons, how much the other's pulling on the electrons. You assign a number that allows you to compare how hard they pull on those electrons. Okay, that's what electronegativity is. It's how hard relative amounts of our relative number, comparing how hard one atom pulls on electrons compared to the other it's combined with. So there's no units of measurement here. Okay, not that I'm aware of. To my understanding, it is that these numbers here, Mr. Lewis, who came up with the Lewis dots in the first place, figured out this relationship and assigned these numbers. Okay? Huh? Electronegativity is a relative measure of how strongly each atom pulls on the electrons that it shares with any other atom. Okay? That's what electronegativity is. All right, so we need to know when that means it's polar, when it's not. Now, there's a difference between a polar bond and a polar molecule. There's a difference between a polar bond and a polar molecule. All right? We're going to first talk about polar bonds. And once we figure out what polar bonds are, we're going to use that to figure out when we have a polar molecule. Okay? You can have polar bonds and not have a polar molecule. Are you listening? You can have polar bonds and not have a polar molecule. All right? You can have nonpolar bonds, and the overall effect is to still create a polar molecule. You can have polar bonds but not have a polar molecule. And given the right conditions, you can have bonds that you would normally say are not polar, but the overall effect still creates a polar molecule. So we have to know what it all means. All right, so we're going to keep it pretty simple. And for us, at least, even though you can have polar molecules when you have a technically nonpolar set of bonds, what we're going to do in here is we're going to only deal with those molecules that are polar because of the polar bonds. But it's still true that you can have polar bonds with no polar molecule. Okay, all right. So let's talk about when we get a polar molecule. We got two atoms here. We got hydrogen atoms and an oxygen atom. We need to figure out the polarity of the bond. Okay, so the polarity of the bond and we're only talking about covalent bonds. It's found by determining. It's determined by finding the difference in electronegativity between the two atoms involved. Okay, so we're going to find the difference. That means we're going to subtract. All right? And then we're going to look at that difference and we're going to assign a polarity or a non-polarity to that. Okay, so what is polarity? Well, a polar bond has an electronegativity difference between 0.5 and 1.5. 0.5 and 1.5. And let's say instead of between, let's say it also includes those amounts. Okay? Including in between 0.5 and 1.5. Okay? Now, having told you that, different textbooks, different chemists, different experts will tell you that those values are different depending on the circumstances. Okay? Some textbooks will say it starts at 0.3. All right? We're just going to keep it at 0.5 and 1.5 to kind of make things kind of simple, to get the idea without making too fine a point on it. Okay? And besides, even if we figure out the bonds are polar, polarity is a relative sort of idea, and it depends on everything else in the molecule. So while we may say it fits this definition of polarity, everything else going on in the molecule can make it less polar or more polar. Okay? So when you get to organic chemistry in college, assuming you go to organic chemistry in college, you'll have to be able to figure out polarity based on these other circumstances. But for right now, this is probably sufficient. This is a beginning place, a place to start. And you'll have to change and modify your understanding of polarity later in the future. Okay? All right. So we're talking about between 0.5 and 1.5. If it's less than 0.5, it's nonpolar. If it's greater than 1.5, it's a whole different category. Okay? So we're going to say that between 0 polarity and 0.5, that range oops, is our nonpolar range. Excuse me. I gave that to you in Unit, the definition of electronegativity was given to you in Unit 2. So go back and look at that, okay? So this range right here is going to be our nonpolar range. So then between 0.5 and 1.5, that's our polar range. And then from that point to infinity, we're going to call that generally ionic. Okay? In other words, the strength, the force by which one atom pulls on the electrons that it shares with another atom becomes so great that we actually get into an ionic range. Now this looks like these are black and white values, that this is definitely nonpolar, this is definitely polar, this is ionic. That's not true. Other circumstances change whether something's polar or nonpolar. So sometimes things will be in the ionic range but not be actually ionic. Okay? Again, we're not going to get into that too deeply here at the high school level. Okay. So let's go back now and let's determine whether the bonds in our water molecule are polar. Okay, so you can find on your periodic table of electronegativities the electronegativity for the two atoms involved and determine whether the bonds are polar. Do that now, please. Go to the periodic table of electronegativities. Using this definition, difference in electronegativity, find out if the bonds, determine if the bonds are polar or not in a water molecule. Okay, Mariah, are the bonds in water polar or not?
No.
Excuse me?
No.
And how did you determine they were not polar? And what difference did you get when you subtracted them? 1.34. And 1.34 then I guess you're saying fits in this range?
Oh, no.
Okay, so if it fits in this range, then what is it? It's polar. Okay? So we're just looking at one bond at a time. Okay? And what we found is that the bonds in a water molecule are polar. This bond is polar, that bond is polar. Now that's not enough to determine if your molecule is polar. You have to have two conditions met to determine this is a polar molecule. Okay? And again, this is a very, very, very simplified way of figuring it out for high school chemistry. Okay? There's a lot more to it than this. We're just kind of simplifying it down to just the simplest possible way we can figure it out. So molecules are polar if both conditions are met. Okay? And the first condition is the bonds are polar. That's the first condition. And we said that condition has been met. The bonds are polar. Okay, but the other condition then is the bonds are unevenly distributed. Okay, the bonds are unevenly distributed. All right. So if we go back to the electron pair shape here, we created that by making all these bonds evenly distributed around that oxygen. Okay? We have 109.5 degrees from any angle, any one of these bond connections, this direct line between the two, between the nuclei here and this electron pair. They're all evenly distributed, 109.5 degrees. So this is evenly distributed, but we got rid of 2 of those to get this shape. Okay? So is this evenly distributed? Come on, it's an obvious answer. Is this evenly distributed? Okay, no. All right. So now the bonds are polar, the bonds are unevenly distributed, therefore this water molecule, by this definition, water is a polar molecule. We've met both conditions. The molecule is polar because the bonds are polar and the bonds are unevenly distributed. Okay? That makes sense to you? Let me further refine unevenly distributed. Okay? Just let me further refine that a bit. All right? Because in some molecules, you have polar bonds and nonpolar bonds. Or you have different kinds of bonds. All right? In order to have a polar molecule, you've got to have the arrangement to be evenly distributed, and you've got to have the same kind of pretty much the same kind of electronegativity going all the way around for it to be nonpolar. Okay? For it to be polar, then, if I have a molecule, let's just use this as an example down here. Let's say I have this molecule where I'm attaching B here and B here, but over here on this side I've got C and C. Okay? If this bond is highly polar and B is the more electronegative element, so there's a pull in that direction. If that's more electronegative than A is and it's pulling in that direction, and this in this direction, then those are polar bonds, right? If I have some nonpolar bonds over here, then these are going to kind of take over. It's still a polar molecule, even though it's a evenly distributed set of bonds, because only the polar bonds are unevenly distributed. Okay? That makes sense? So it's not just the bonds, really. It's the polarity that's unevenly distributed. Okay? So we might ought to refine that to say it's the polarity. We're starting out with bonds, but later in this unit, if we get to situations where we have an uneven distribution of the polarity, then we can have a polar molecule, even though you have an even distribution of bonds. Does that make sense? It's all about the polarity. Okay? All right. Having done that, now it's time for you guys to practice. All right. Do you guys remember the formula for ammonia? What? NH3. So I want you and to practice using this process. Work with a neighbor, find a learning partner, figure out the shape of the molecule, figure out if the bonds are polar, figure out if the molecule is evenly or unevenly distributed, and make a determination, make a claim and justification. Claim and justification, is this molecule polar? Okay? Ammonia. Is ammonia, which is NH3, is that molecule polar or not? All right, so we're going to have a student serving as our guest teacher. Okay, see how he did. And look, your job is not just to sit back and wait. Your job, as other students in the class, is to watch what he does, see what he does, ask questions if necessary, help him out if he gets off track. Okay? This is a group learning experience, not just one person showing you how it's done. Okay? Can you slide that over so people can see?
Oh, sorry.
That's okay. You're good. So he's got a sharing arrangement and then the Lewis dot formula. And he's working on his shapes here. Okay. So how's he looking so far, guys? You think he's good? Okay.
I got a little close.
bit there.
Oh.
So he's got this molecular shape then. So now he's determining if he has polar bonds. Okay, so he's determined the bonds are polar because they're between 1.5 and 0.5, and he says the molecule is unevenly distributed. So what's your claim about the molecule?
Do I need to write it down here?
Yeah. Is it polar or non-polar?
Oh, well, that's what that was polar. Here.
But is the molecule polar?
Oh, molecule? Oh, yes.
Okay, since it meets both conditions, he's got a polar bond, or three polar bonds. He's got the bonds being unevenly distributed, and he's saying that's enough to claim that the molecule is polar. He's right.
How do you spell molecule?
M-O-L-E-C-U-L-A-R.
Molecule?
Polar, or molecule is E, I'm sorry, that's right. Okay? Polar molecule. All right. Did a good job. Yes?
How do you get this number for when it's
From the periodic table of electronegativities. You get the... So here's nitrogen, 3.04. Oxygen is 2.1. That's what he got here. Now what he didn't show, that you should show in here, and this is a kind of a side issue for this, but it's important. It's going to be counting off points if you don't show all of your work, and that means you have to round off this last number over here. This is an unusual looking 4, some kind of, I don't know, German cross thing going on here. Okay? But you need to underline that last digit over here. I'm just picking at you. It's fine. You can tell, very clearly tell it's a 4. You need to underline that last digit and round it off to 0.9. Okay? Okay. So what I'd like to do here is to just clear this up a bit so that there's no confusion about what these numbers are. Let's say this is the electronegativity, En, for nitrogen. So I got nitrogen as a subscript. That's what that number is. Electronegativity for nitrogen. This is the electronegativity for hydrogen right here. Okay, or you could use an arrow pointing to it. As long as you show that's what those things are. Because there are no units of measurement for electronegativity. You don't have to have any units of measurement, but you do have to show what it applies to. Okay, don't leave people hanging wondering, what is this? Okay, tell them what it means. So this is electronegativity difference, okay? So let's say that's END, electronegativity difference, for a bond between nitrogen and hydrogen. So I'm going to put into the subscript position N2H. You could say H to N, doesn't really matter. Okay? Just to be clear, that's what it means. All right? So 0.94 electronegativity difference for an N2H bond is uneven, and it's unevenly distributed, so that's those two things, both conditions are met. A plus sign, or you could use a semicolon if you wanted to. All right, a lot of ways to say that, okay? But those are two different ideas. Make sure you separate them somehow, a slash between them, something, okay? And when you say it's a polar molecule, that's great. That's your claim, okay? So this is a claim. Your justification is because, and then you tell me what because is. Because the bonds are polar and the molecule is unevenly distributed. So when you do when you claim it's a polar molecule, it's not enough to claim it. Okay, you have to claim it and tell me how you know that to be the case. All right, claim and justification. You got that? All right, good. Let's try something else, okay? Let's practice with this one. Carbon tetrachloride. Carbon tetrachloride. So we're kind of putting together some things here from this unit. First of all, I'm giving you a name. You have to figure out the formula. Okay? Then you have to tie in stuff from previous units where you figure out the sharing arrangement, Lewis dot formula, electron pair shape, okay, then the modified electron pair shape, the molecular shape, then you have to do this new stuff, okay? So we're putting together, we're starting to see why chemistry is so cumulative. You have to know the stuff from the first unit to be able to do all the other units. You have to know the stuff from unit 10 to do the stuff, because we took 10 out of order, to know all this other stuff. You have to know the stuff from unit 2 and 3 to do what we're in now, unit 4, okay? So let's work on this problem here, see if you can figure out the polarity. Work with a learning partner. You can choose your own. And then we'll come back and somebody, it might be me, it might be a student who decides to do it. All right, so we're going to use another guest teacher, another student, who's going to show us his work and then claim and justification, sharpening his skills for college. We're starting out with the electron dot formulas for the carbon and all 4 chlorines. Let's see. Okay, and now he's doing the sharing arrangement. So we have a sharing arrangement for carbon tetrachloride now. This is the Lewis dot formula. Okay. So he's going to a 3-dimensional arrangement here now. This is going to be his electron pair shape. Probably shouldn't speak before I actually see the electron pairs, but that's what it is. So I said, what's the name of this geometry? Tetrahedral. Okay, good. A tetrahedral electron pair shape. Now he's redrawing the exact same shape. And he's replacing any sets of electrons in the Lewis dot formula that are shared. He's replacing those electron pairs with the symbol for the element that goes there, shared with.
Repeat it.
Hmm?
Can we repeat it like that?
No.
Okay.
That's the end of the drawing. Now we've got to figure out what your shape, what your claim and justification is. So there's no modified electron pair shape here because there were no lone pairs on that carbon. Okay, the carbon had no lone pairs. So you're saying these bonds are have a 0.6 electronegativity difference? Where's your work to show that? I don't want you to just say it's 0.6, okay? I want you to tell me, show me the work, okay? Got that? I don't know. We're going to find out, okay? Because he's going to show us on paper, okay? I got that. Now, which one of what do those numbers apply to?
The top one is chlorine.
Okay, so you need to label that somehow so I can see that. Okay, and I showed you how to label those up here. All right, in the previous problem.
Okay. Don't you round this one?
Well, first thing you need to do is say this is capital E, capital N, subscript CL. So I know that's the, let me show you this. Let me show you. Up here I said we wanted to do it that way. This is electronegativity for nitrogen. Do the same thing for the chlorine here and the carbon. So subscript Cl, because that's for chlorine. Okay, good. All right, and now tell me what that number at the bottom is.
Yeah,
I don't mean, no, you don't need to round it off. There's no empty slots above that 1.
0.64
Well, what is that?
polar. It's in between.
But that you judge it to be polar, but what is that number? I did it up here. That's the electronegativity difference for your bond. Would you label it that way, please?
Okay.
Let's get rid of your underline 1, because that underline doesn't belong there. You only round off if you're adding and subtracting if there are empty slots above it. Okay? So while I know you guys can add without putting things vertically, we're going to go back to first, second, and third grades where you had to add everything vertically. So you can see how to round off properly, okay? So that's not nitrogen to hydrogen there. That's chlorine to carbon. Just draw a line through it.
Okay.
And put chlorine to carbon. There you go. That's good. That's good. All right, now, he says it's polar, but you've made a claim, but you don't have a justification. What's your justification?
It's in between 0.5 and 1.5. 0.61.
All right, so your claim is this is a polar molecule. That's your claim. What you have is there's some numbers and a statement, but you haven't really explained what that means. Okay, so what you're going to do is you're going to say this is a polar molecule. That's your claim, and then you're going to say because I have both an uneven distribution of bonds and I have a polar molecule. That's what you're going to say, but you don't have an uneven distribution.
I don't.
Do y'all see what I'm talking about? Ask somebody. Have them help you. Help him out, guys. Explain it to him.
It is.
He did, but he claims it's polar. He claims it's polar,
You can't have polar.
but he doesn't have the justification for that.
It's polar, but it's not a polar molecule.
It got polar bonds, but not a polar molecule. So your claim is, what your claim should be, is that this is not a polar molecule. Because while we do have polar bonds, we don't also have an uneven distribution of those polar bonds. That make sense? Because you got to have both. If you don't have both, you don't have what you need.
We do this one time.
For not polarity, we have.
I thought we showed us at one time.
Oh, I showed you what it might be in other circumstances, but I haven't done this particular kind of molecule yet. Okay? So write out your claim and justification. Let's revise that. So put a line through polar, one line. Okay? And let's revise your claim and justification. You're claiming it's a polar. Well, you haven't claimed anything yet.
Well, it's not a polar molecule.
That's
but
right.
Has,
So it's a non-polar molecule
but has polar bonds.
with polar bonds. That's right. It's a non-polar molecule with polar bonds. But that's still not your justification for claiming it's non-polar.
So even with the number, it still wouldn't be specific.
You've got to put it down in a sentence that's clear and convincing. Okay?
I'm talking about like the term at the polar.
Hello? Okay. Uh-huh.
You said my justification.
This is a nonpolar molecule with polar bonds. It's nonpolar because the bonds are not unevenly distributed.
Okay.
Or you could say, you could say it in a more positive way and say the bonds, it's nonpolar because the bonds are evenly distributed. Okay? Let me borrow this a minute. Okay? You got it kind of getting it? Okay, good. All right, good job.
What did I bring up here?
I don't know what you brought up here. Are y'all beginning to get it a better handle on things now? Good.
So even if the number, it was polar, but it's non-polar, because it's
Right. You got to have both. You got to meet both conditions. For a molecule to be polar, we said that you have to have both conditions met. Okay? You have to have both polar bonds and an unevenly distributed set of polar bonds.
So we only have one of those.
In this case, we have one of those, yes. We didn't have both. Okay? If you don't have both, you don't have what you need. Okay? So there are a handful of molecules, a handful of compounds that you need to know the name for, and by just the name. Okay, one of those is water, another of those is ammonia. You need to know the ions of ammonium, for example. But we've gotten far enough now into organic chemistry that you should be able to figure out the actual chemical formula for this molecule. Okay, so there's our first one. You're going to figure out whether it's polar or not. And then, let's see here. How about we do, all right, stretch you a little bit here. I haven't actually done one like this, but I have given you all the information you need to be able to make this just claim and justification in here, okay? And let's see. How about we do, all right. Got that?
So the second one,
These two right here, we haven't actually done one like that, but I told you about those, where we have more than one kind of atom around the central atom here. Okay? Here we go. Remember when I said we had something like this, where I had some, this might be polar in this direction, but non-polar over here. Okay? And it might be also that it's polar going in this direction and polar going in that direction, so they kind of cancel each other out. You got to make a judgment about that. Okay? Look at the structure and try to figure it out. All right? So while you're writing those down, let me give you a couple of things to help you, that might help you. You don't really need them, but it might help you. Okay? If I want to show a bond that's polar, so if I want to show this is a polar bond between A and B, I'm going to draw an arrow in the direction of the more electronegative element. Okay, and I'm going to put a kind of a plus sign on the end of this one. Okay, so this end over here is less electronegative, and this one is more electronegative. Okay, now you don't have to have that, but it might be a tool that will help you figure it out to put everything together. Okay. It's also true that if you have a polar bond, A going to B, that the result is that this end of the molecule is partially positive, and this one is partially negative, because the electronegativity is greater over here. Okay? And the way you show partially positive or negative, this means partially positive and partially negative. So it's like a capital S with the bottom end sort of closed up on it. Or if you guys are in music, anybody in music in here, you know how to do a treble clef symbol? Okay, it's kind of like that, but without the part that goes down the middle of it, right? Kind of. These. So a treble clef looks something like this. Right? So it's kind of part of that. Y'all never did that before in music?
Yeah.
Okay. I mean, I'm just trying to give you some relationships to help you remember how to do that. I like the S with the back end closed up. What you want to go to the left? What, this? Okay, how's that? All right, everybody good? All right, so you got a few minutes to start. Okay, if it were me, because I know that these two are a little bit harder, I'd pick one of these to start with right now while I've got other people in class with you and you've got me in here, and at least you can get kind of a head start on the direction you need to go in, okay?